Brønsted Lowry acid-base pairs. So in a Brønsted Lowry reaction, just a reminder that you have to have an acid and a base because we're transferring a proton from one thing to the other. So something gives, something receives. And the acid and the base then are formed as a product. So the base becomes an acid as a product. So if you look at it this way, HA is just a way of being able to say a generic acid. I have the hydrogen in the front, which is all that matters. And B minus is a generic base. So the generic reaction is that this hydrogen ion leaves the generic acid and joins the base. So the generic acid loses that, loses the H and a positive charge, and it becomes A negative. And the generic base, B minus, gains that proton, so it has one more hydrogen than it used to, and the charge is increased by positive 1. Well, if I result in an HB, then technically I could re-give that proton back up, acting like an acid. And if I am A minus, because I lost my proton, I could, in theory, grab another hydrogen ion and re-establish that HA so I could act as a base. So an acid as a reactant generates a base when it gives up its proton, and the generic base, when it grabs that proton or accepts it, generates an acid on the other side. So we call anything that is a product a conjugate. Conjugate means product. And that goes with what it came with. So a base will create a conjugate acid, and an acid will create a conjugate base. So conjugate always refers to what I'm creating. Acid creates a conjugate base, base creates a conjugate acid when it's received that proton. So these are called conjugate acid-base pairs. They differ by one proton. The acid and the conjugate base, the acid has that proton, the base doesn't, conjugate base. And here my base doesn't have the proton, but when it's gained it, the conjugate acid has that proton. So I can look at it in a specific circumstance. Here, water acts as an acid. It gives its proton up and becomes OH minus. So the conjugate acid-base pair is H2O, and its conjugate base is OH minus. NH3 accepts that proton that H2O gave up, and as a result, it creates its conjugate acid of NH4 plus. So again, H2O and its conjugate base, H2O has one more H and a one more positive charge. The base, when it becomes a conjugate acid, has one more positive charge and one more hydrogen. So remember, I'm always transferring a hydrogen and that positive charge. So it's not just my subscript that changes, but it's also the charge that changes. Here's another example. I have HNO3 that gives its proton up to the base F minus. So F minus, when it gains that proton, I have an H now, and my negative charge becomes neutral. This F base, F minus base, becomes the conjugate acid HF. HNO3, when it's lost its proton, becomes the conjugate base as the nitrate ion. So Brønsted Lowry acids and bases don't require the base to have hydroxide ions, but they have to interact, they have to be in pairs. So it's expanding the definition. Now F minus or NH3 can act as bases, and we know that they do because they affect the pH. And it's more of this transfer between what was an acid and what could accept my proton from that acid.